Okay, these are actual AP problems here. And okay, so for this one, there's going to be a, let's say a tension 1, and there's going to be a weight force down this way that's smaller than that, so that'll be mg, and this will have a tension 2, and this will have a weight force down that's bigger than that one, so the 2 mg. Okay. Alright, so for this one, that would be MA equals tension 1 minus mg. And for the other one, it would be 2 MA equals 2 mg minus T2. And we could draw a force diagram for this object here. It would be a tension 1 down and a tension 2 down. There would also be a force upward here, but it's through the pivot point, so we can kind of ignore that to draw or write this other equation for rotational motion. So that would be, for the second part of this, the net torque, which is I alpha, is equal to T2R minus T1R, or I think I'll write it like this, T2 minus T1 times R. And I think I may go a little bit further than that. This is going to be 1.5 mr squared A over R equals T2 minus T1 R. The R cancels the square, this R cancels that, and so I have 1/2 the mass, and that's going to be 1.5 times the mass, and that mass is 3m times A equals T2 minus T1. Oh, sorry, T2 minus T1. Okay, so we have to solve for the acceleration now. Notice I have a negative T1, positive T1. I have a positive T2, negative T2. So I could add up all three equations here. This is 3/2, so that's really going to be 9/2 MA plus MA plus 2MA. So this is 2/2, and this would be 4/2, and this is 9/2. So 9, 13, 14, 15, so 15/2. 15/2 MA equals, it's going to be 2 mg minus mg, which is just simply mg. The m's will cancel, and so A equals 2/15 of 10, or of g. I'm not sure if we should use 10 or not. We could probably go ahead and put 10 in here. So this would be 2, so it's going to be 4/3 meters per second squared. Determine the tension in segment of the cord attached to M. Okay, well, once I know what the acceleration is, I can plug that back in over here, and so that would give us then the tension, so this is D. I think I'm going to leave it in terms of 2/15 G to plug it in here. So that's going to be 2/15 mg equals T1 minus mg. That's 15/15 added over, so that would be 17/15 mg. That's what the tension 1 is. Then it says determine the normal force exerted on the apparatus by the table. Okay. So coming back up to this, remember how I said there was this force upward? That force upward is going to be equal to sum of T1 and T2. And then if you're thinking about then this apparatus here, actually, that's not true. It's not going to be sum of T1 plus T2. This also has weight, so there's a weight downward. So that normal upward is going to be equal to T1 plus T2 plus the weight of 3m, so 3mg. Anyway, that reaction force upward is going to be balanced, or it's going to have an equal and opposite reactionary force downward. And so thinking about the force diagram for this, it would be that force plus this weight of this thing here too. So let's come back up here and figure out what this force would be. This force here is going to be equal to, let's call this the normal, I guess, is equal to the weight of 3 mg plus, it'd be T1 plus T2. We just found T1 to be the 17/15 mg. We could also figure out what T2 is. T2 is going to be equal to 2 mg minus 2 ma, where A is 2/15 G. So I guess it'd be minus 4/15 mg minus 4/15 mg. So this would be 30/15. So this is going to be 16/15 mg. That's what T2 is. Something seems wrong there. So we found that means T1 is bigger than T2. Uh-oh. Where's my mistake at? Okay, I think right here's my mistake. I shouldn't have put in 3m here. It was just simply 1.5 mr squared. So this is 3/2 ma. And then adding these together. So this is 3/2. This would be 4/2. Okay, so adding these together, I have 7, 8, 9, 9/2 ma equals mg. M's cancel, so that means A would be 2/9 g. 2/9 g. Okay, then coming back over here to figure out T1. So I'm going to plug in 2/9 g for A. And so it's going to be 2/9 mg. 2/9 mg. And so 9/9, so that's going to be 11/9. 11/9. All right, so let's come up here and make this 11/9. All right, then T2, let's see, T2 is going to be 2mg minus, and this was 2. All right, so 2/9 g, so that's going to be 4/9 mg, so minus 4/9 mg. All right, 9, so it's 18/9. All right, so 18 minus 4 would be 14. 14/9 mg. Yes, that sounds better because T2 now is bigger than T1. Whew, that was scary. All right, plus 14/9 mg. So we just figured out what this normal force is. And so now when we find the normal force down here, it's going to be that same force pushing down plus an extra amount of weight here, so 4 mg. So it's going to be plus 4 mg. It's going to be our answer for E. This is going to be the answer for E. So let's see, common denominator is 9, that's 36, 9, and that's 27. So let's see here, 40, 50, and so 88. I believe it's 88. 88/9 mg. So that would be the normal force on this whole apparatus. So if you notice that, that's going to be less than the weight of the whole thing. So this is 4, that's 7, 8, 9, 10. So 10, 10 mg, which would be 90/9 mg. So that's a little bit less than the weight of the whole thing. And that's because it's accelerating. All right. So I don't remember what year AP exam that was, but that's one problem. There was another AP question like this, but I went ahead and put some numbers to it. So let's see here. All right. Okay, looking at the torque of this, we could draw a force diagram for this object here, and I'll call this a T1 up, and it has a weight down. I can draw a force diagram for this as well. There would be a force up at the pivot point, but that's not going to really cause the rotation. There's going to be a tension force this way. I'm going to call this tension 2. And then on this object here, there's two tensions. There's a tension 1 that's the same length as this one that's longer than tension 2. And there's a tension 2 this way, tension 2. Okay, I think for the big object here, I'm going to say that I alpha, is equal to tension 2 times the radius of 0.52. The rotational inertia, they tell us, is 247. So 247 times A over R, so A over 0.52 equals tension 2 times 0.52. So I have two unknowns. All right. Coming to this one here, this is going to be I alpha, which is 14 for I. So it's going to be 14 times A, same acceleration, over its radius, which is 0.09, equals tension 1 minus tension 2 times 0.09. So now I have three unknowns. I have three unknowns. I've got A, I have T1, T2. So I need one more equation, and that's going to come from this one here, and that's going to be 895A, that's MA, equals the weight of this, 8,950 minus T1. So I think what I'm going to do is I'm going to divide this equation by 0.09, so that's going 0.09 squared. I'm going to divide this equation by 0.52, so 0.52 squared here. And the reason why I did that is because if you notice here, I have positive T1, negative T1. Here I have negative T2, positive T2. So I can add these three equations together. There won't be any T1s or T2s, and there will only be A for acceleration. And so I can figure out what the acceleration. Once I know the acceleration and I know the distance, then I can use kinematics to figure out what the speed is when it starts from rest. Okay, here's another AP problem. Okay, so from this, it's being held there on this pivot. So there's a force upward here. Let's call this the force from the axis. There's going to be a weight force, X right in the center of this. And there's going to be a force upward from the thread here, or from the thread. So that force, when it's held in this perfectly horizontal position, and this weight is acting right in the center, half of that is going to be, this is going to be exactly half the magnitude of the weight. So that would just simply be mg divided by 2. So mg over 2. If it was closer to this end, then I could not assume those two would be the same. I'd have to do torque, and which you could still do torque right now if you want to. You could say the pivot here, and so the torque from this force, so that would be force times the length times the sine of 90 has to be equal to the weight times this length, which is L over 2, times the sine of 90. The L's cancel, and you see that that force has to be exactly half the weight. Okay. In fact, I would say you probably need to show that. I don't know. This is probably only worth 2 points. That's probably 1. This is the second point probably. All right, so this thread breaks, and we're supposed to figure out the angular acceleration immediately after it breaks. So in this position, now I'm going to put the pivot down here. In this position down here, the only force causing torque is the weight. And so the torque would be equal to the weight times the distance away, L over 2, times the sine of 90. That's also equal to I alpha. And they tell me what I is about the end. So that's going to be L squared over 3 times alpha. We're trying to find the angular acceleration. And that's going to be equal to mg L over 2. So the m's will cancel, one of the l's cancels, and so I'm going to get the angular acceleration is equal to, let's see, multiply both sides by 3, divide both sides by L, so it's going to be 3 halves g over L, and that's our answer to B. C, the translational acceleration at the end of the rod. Well, of course, we know that A is equal to R alpha, and so it's just simply going to be the length, that's the R, times that alpha we just found. So times 3 halves G over L. The L's cancel, and so we get 3 halves of G. The force exerted on the end of the rod by the axis. Okay, well, it's not translating, so the net force has to be 0. And so that means the force at the axis has to be equal to the weight. And so I think we're just simply, I think it's probably a 1-point question. It's just simply going to be mg. It has angular acceleration, but there's no translational acceleration, so therefore the net force has to be 0. All right, the last question. This is also an AP question. This one's kind of a tough one, so if I remember correctly, I think I remember this being the hardest one. And the reason is because I think at first, it has 2 different motions. Its motion gradually changes from pure translation. That means it's sliding across here. It's not rolling. Through rolling with slipping, and then eventually just rolling. There's no slipping. So we're going to say this is where it starts to roll. So there's slipping with rolling. So we're supposed to draw a force diagram. So there's going to be a normal force right here, normal. There's going to be a weight force, the X right here, weight. These two are balanced. And there's going to be a static friction force, right? Not static. At first, while it's slipping, that's going to be a kinetic friction force that's causing it to slip. And that's what's going to end up causing the rotation. Okay. Net force on the ball during the rolling with slipping. All right, so the net force must be from the friction, and it tells us the coefficient of sliding friction. So for B here, to find the net force, it's just simply going to be the net force is equal to the kinetic friction. And so it's just simply going to be 0.45 times the, do we know the mass? Oh, yeah, sorry. Times the mass times 10. So that's going to be the net force. Okay, so for C, once we know what the net force is here, so I think I'm going to have to go a little bit further, equals mu times mg, the m's cancel. So I'm actually working on part C, so you're going to have to figure out what that net force is. But for C, we have to find the linear velocity as a function of time. Well, that means we need to know what that acceleration is. And that acceleration, by the way, is negative. It's slowing down. So now I can do kinematics. The velocity as a function of time, that's the final velocity, would be equal to the initial velocity, which is 3, minus mu, which I guess they give that to us, times g times t. And so that would be 3 minus 4.5 t. That's the velocity as a function of time. Okay, then define the net torque. The only force up here that causes a torque is the friction, because the normal goes right through the center, the weight goes right through the center, so it's only the friction. So the torque would be given by the force of friction times the distance away, which is the radius, times the sine of 90. And so we found the friction over here, and we know what the radius is, put that in meters, and so I could figure out what that torque would be. All right, so this is going to be, okay, now I'm getting ready to work for E. So for E, I'm trying to figure out the angular velocity as a function of time. Well, that means I need to kind of know what the acceleration is. So they tell me what I is. So the angular acceleration, I times alpha, is equal to, let's see, u, k, times mg times r. And so that means that alpha is going to be equal to mu k, which they give us, times the mass, which they give us, times g times the radius, which they give us, divided by I, which they give us. So if I know what the angular acceleration is, that means that omega, I'm going to use Vf equals Vi plus At. The initial velocity, angular velocity, is 0. So I just simply take my angular acceleration that I can calculate and get a number times t, and that's it. Determine the time at which the ball begins to roll without slipping. Okay, so it's going to roll without slipping once the, remember that omega is equal to V over R. Well, so this is a function of the velocity, the translational velocity, and this is a function of the angular velocity. So if I plug this in, to V here and solve for T, that will give me the time at which it's going to be purely just rolling. Okay, determine how far. So once I know how much time it took to get to the point where it's doing pure rolling, no more slipping, then I can go back and do kinematics here. I can plug that time in here to figure out what that velocity, or actually I could plug it in here too, but anyway, I can find that velocity and I can just do kinematics. I know what the initial velocity is and I know what that final velocity is. I know what the acceleration is in between, and I kind of know everything. I know the time. I need to find that distance then. So I'm going to do regular kinematics then to figure that out.